Welcome to today's webinar. Our topic will be the timber arch structure design per EC5 in RFEMu. We will model this structure on the right, show how the loads are applied, and then do the design. My name is Moritz Bertram, and I will lead through the webinar today. My colleague Bastian Kuhn, who is also in charge of the timber modules, will answer your questions. You can ask questions using the control panel, which you can show and hide, usually on the right side of your screen. And you can type in your questions in the corresponding box down here. Also, you can adjust your audio device in the control panel if necessary. Should your question not be answered during the webinar, we will send you a follow-up email with the answer later on. Now we will have a quick look at our agenda today. We will have a brief look at the options for timber design using our software. Then we will do the modeling and loading of an arched timber structure in RFEMu. And in the end, we do the design of the timber components in RFTimber Pro. Let's have a look at the timber design add-on modules. Here we have the module RF or just Timber Pro, always depending on if it's for RFEMu or RStab. With this module, we can do a design for timber members per Eurocode 5 or the Swiss standard SAA 265. Then we have the module RF Laminate for the design of laminate surfaces. We have several modules for different standards, the US standard, Canadian, Brazilian, and South African standard. And today we will use the module RF Timber Pro. Then we have several modules for the design of timber joints. First is RF Joints Timber, steel to timber, which can do a design of indirect connections per Eurocode 5 and American standards. Then the module RF Joints Timber, timber to timber, for the design of direct connections per Eurocode 5. And then we have RF Limits, which does a comparison of results with defined limit states with timber fasteners by Shiga, Sherpa, Wirth, Simpson Strong Tie, Knapp, and Pitzel. And then we have a module family or program family called RX Timber with the program RX Timber glued laminated beams, then continuous beams, a module or a program for timber columns, one for coupled purlins and continuous beams. Then we have the program frame for the design of 3-hinged frames with finger joint connections. We have the design for truss bracing for stiffening, and we have the module RX Timber Roof for the design of monopitch and dual pitch roofs. All of these are available for Eurocode 5. Then let's have a look at the at RFEMu, and here we will now make a new model. It's supposed to be a timber arch structure. It's a 3D model, and we will do the classification of load cases and combinations according to the Eurocode with Eurocode 5 for timber and the national annex for Germany. And we will create our combinations automatically. Let's have a quick look at the coefficients, the partial safety factors, and the combination coefficients are fixed. but we can do changes for the factors of the construction. We will keep the consequences class at number 2, and for the deformation coefficient for timber structures, we will select the service class number 1 for 20 degrees Celsius and about 65% humidity. So it's not very humid environment. Okay, we make this new structure. You've already seen it, but I want to show how to model, so we go in here. At first, I will make a line from 0, 0, 0 over x 10 meters, z minus 5, so it's upwards, and x 20 meters, z 0. Let's look at that from minus y. So now we have this line, and if we edit the line, we can select the register member, make a member available at this line. This is supposed to be a beam, which gets a new cross-section. The cross-section is supposed to be a parametric rectangular timber cross-section with a width of 140 millimeters and the height of 440 millimeters. The material is supposed to be glulam timber GL 28C according to the German Eurocode. Okay. The member is not supposed to be rotated. Okay. So that's what it looks like. And we want to have supports at both ends. So I select both of the end nodes and apply a new nodal support. The support is supposed to be fixed in X, Y, and Z direction, and it's supposed to have a restraint around Z direction. Okay, so we have supports. Next, we will divide this. Oh no, at first I make a new set of members out of that. So right click on the member, select create set of members. Okay, so I already have that, and if I now divide the line or the member and copy it, so it's always there, and it's also copied with the structure. So right click, I want to divide this member into 3 equal parts. I use the option divide member with n intermediate nodes for that. And if I have 2 intermediate nodes, then I get 3 equal parts. And now I can copy these 3 members with their supports. And while copying that, it's supposed to be 5 copies, 5 meters in Y direction for each span. And if I use the expanded settings for these copy functions, I can create lines between nodes and new members between these nodes. So now as templates, I would only have the rectangle 140 by 440. That's not what I want. I want a new member as template. So I have to create a new member. And this coupling between these girders is supposed to be a truss. Gets a rectangular timber section with a width of 120 millimeters and a height of 120 millimeters. the material is the same as before. Okay, 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 okay. So that's almost our structure. I delete the lowest couplings because I don't need them here. And I want to divide all these members at their intermediate nodes where the couplings are attached. And for that, I use the function connect lines or members. So click that, draw a box around that, and most of the girders are divided. I don't know why not all. These two are not. Now they are divided. Okay, so we got that. Now we want to rotate these couplings so their top edge is parallel to the top edge or the edges of the girders. So I'll select these, right click on one of them, member, edit. And I want to rotate these members using the center node of one of these curved beams. For that, I at first have to create this center node. So I click on this button. Now, where's my center node? If I go on display, the display navigator, and lines, I have here the point center points. I click that, and now you can see that these center points are shown. And I can select one of these. Now there's a new node being created. In this case, its number is 77. And I want to direct the plane XZ to this node. So that's what this says. Click OK. And as you can see now, all these top edges are parallel to this, to the edges of the girders. Okay, what else do we need? We need a bracing for the structure. For that, I look from the top, tilt it a little so I get everything right. And I change my view to the wireframe view and create some more members. In this case, they're supposed to be tension members with a new cross section. It's supposed to be a steel cross section, a solid cross section. A round bar with a diameter of 16 millimeters, and the material is supposed to be steel S235. Okay, okay. I use this second span here, and I add these bracings manually since it wouldn't make sense to use some functions for that, because I'm not going to be any quicker than that. Okay, now I'm pretty much done with my construction. The only thing I still want to do, I'll change back to my solid transparent model. I'll select this gable, and I want to add in some gable columns. View in -y direction again. Now I select this bottom node with a support and copy that. I copy it by 5 meters in X direction and make 3 copies. And don't forget to turn off the connections between the nodes. I don't want them now. Okay, I got these bottom nodes for the gable columns. And I make another beam, another cross-section. Cross-section type is supposed to be rectangular timber cross-section again, with a width of 100 millimeter and a height of 200 millimeters. Material is the glue-lime timber again. And they are supposed to be rotated by 90 degrees. Oh, that was not correct. No. Again. So this is part of my beams. These have to be rotated. And now I want to extend these members up to the girder. And so I want to extend these members to the next member or line. And I want to divide the target member. And I want to extend on the member end. Okay, so these three columns are going up to the girder now. The last thing I want to do to these columns is get them a hinge at the top. So I want to edit them because they're not supposed to take up any normal forces. Later on, you could just take them out because you want to extend your building, and so they don't have anything to do with the total stability of the building. Okay, now I got these three columns, and I want to copy them to the other end of the building. To cancel the visibility mode for that, make one copy from one end to another, 25 meters. Okay, and I have my gable columns. So before we can start adding the loads to the building, we have to show the numbering, because for the loads it's sometimes important that the numbering is ascending. For a load, a member list, so in this case we have member number 1, 7, 77, 2, so this is not ascending. So I can select everything, go to Tools, renumber automatically, and now I have to select the priority in which I want to do the numbering. My main priority is supposed to be on the y-axis in positive direction. Then the second priority lies on the x direction, also positive, and the third on z direction, also positive. Okay, so now we have 1, 2, 4, 5, 3 is the column. So it's not consecutively, but ascending, and that'll be enough for our purposes. Okay, now we can go ahead with the loading. I'll add a new load case. This the first load case is supposed to be self-weight, and I want to add the roof weight to that. So I add roof system. This is permanent, and the self-weight is active, so it's calculated by the program, and the load duration is permanent. Okay, and I need to add some loads for the membrane roof I have on here. So I make a new member load, reference that to the sets of members, and relate it to the true member length. It's supposed to be 1.5 kilonewtons per meter for the inner girders, and for the outer ones we will cut that in half. So it's 0.75. That's what it looks like. Then we go on with a second load case. This is supposed to be snow, short term. And we can go ahead. Pretty much the same, although we now relate the load to the projected member length, which is the correct one for snow. It's a uniform force of 3.4 kilonewtons per meter. Yeah. I'll just show you again on the PowerPoint presentation. So we have a load, uniformly distributed load according to Eurocode for arched roofs, and this adds up to 3.4 kilonewtons per meter. So I change back and add these loads to the structure, to the inner girders, and you see it's kind of like stairs on here. That depends on the closest distance to the members, so it just looks a little funny, but it's correct. And for the end girders, I cut that in half again. Okay, next load case is supposed to be snow drift. So we have 0 at the beginning, 8.5 at the quarter, then in the middle again 0, half of the 8.5 on the other side, and so on. And we change back. And have to make a new load case. This is snow, and it's snow drift. Short term again. And in this case, it's supposed to be varying. So at 0, I want to have 0. Then at 5 meters, it's supposed to be 8.5. At 10 meters, it's 0 again. At 15, it's 4.25. And at 20 meters, it's 0 again. So that's what it looks like. Click OK. And I add that to these girders. Looks similar to the other snow, but yeah, it's got these pyramids, and we cut that in half again for the ends. So 4.25 and 2.125. Okay, that looks good. And we can go on to the next load case. Next load case is supposed to be wind in lateral direction in +x direction. And I'll show you in the presentation. This means that we have wind pressure in zone A, wind suction in zone B, and smaller wind suction in zone C. And that's all. That's again being done with the varying loads. So I go back to sets of members, varying. In this case, we shouldn't use absolute values for the length, but go with relative values. Makes things a lot easier. So we go with 25 again, because we got two values in this place, then 75 again, and 100. And we go up to 1.3, 1.3, minus 3.1, minus 3.1, minus 1.3, and minus 1.3 again. Okay, and got a mistake in there. So I go back. Oh, I hope I haven't done anything stupid. No, still everything fine. I have forgot to direct that to the true member length, C direction. So that's still in there. And that's what it's supposed to look like. Then half of that on the gables. So 0.65 minus 1.55 minus 1.55 and minus 0.65 twice. That's what it's supposed to look like. Actually, I should add a few more horizontal loads on the gables now, on the gable columns, and horizontal loads on the girders, but that would take about 7 to 10 more minutes more, and I don't want to bore you, so I've done that in another file. I'll show you when I'm done with that, and I go ahead and add another load case. Load case 5 is wind in longitudinal direction. There's always wind suction on that, so minus 2.3, all acting upwards. And I'll go back and add these loads, not varying in this case, but minus 2.3, related to the true member length. Like that, and half of that on the gables again. So minus 1.15. Okay, so we got that. Here it's also the case that I get other horizontal loads on the gables, and I'll show you later on. Last load case is imperfections towards plus y. So we want to add a new imperfection in local y-axis according to Eurocode 5, and it's supposed to be a pre-camber of 1/400 of the length of this girder, and this is applied to, oh, no good. I'll do it again, and I have to reference it to the sets of members, of course. Oh, that was wrong. So this looks good. And now we can go into the combination. So I go in here. Here I can have a look at my load cases again. Then I go on with actions. I have permanent loads, I have snow loads, and I have wind loads. Please keep in mind that you want to put these snow and wind loads alternatively for this model. And then we can go on with combination expressions. Here we have 4 default combination expressions, 1 for the ultimate limit states and 3 for the serviceability limit states. We want to calculate the ultimate limit state per second order analysis or the p-delta method. And the serviceability limit state is supposed to be calculated using a geometrically linear analysis. Also, I have to apply my imperfections, but I just have to use it for the ultimate limit state. So I activate differently for each combination expression, and I activate the imperfections for the ultimate limit state. Window opens, and now I want to use these imperfections. I can stick with the default settings here and click OK. For the serviceability, this is not taken into account now. Now I go to action combinations. Here I see the combinations of the different actions, and I also see that the k-def factor is applied for the quasi-permanent and the characteristic quasi-permanent loads. So it's 1.0 plus 0.6 for the permanent loads. I go ahead and create the combinations for load case 40. I get 40 load combinations, sorry. And then I have my result combinations, which get me the minimum and the maximum out of all combinations I have made. Okay, so much for the combinations. The last thing I have to add here is that we have to have a look at the global calculation parameters, because we have members that are nonlinear due to their member type. In this case, the tangent members. We should turn on the exceptional handling for failing members to be removed individually, because if 2 or more members fail at the same time, the system is going to be unstable, and that will mean that we can't get any results, we can't do the calculation. So we have to turn that on. Okay, now I'll switch to my other model where I have already applied the full loading for the wind. You see that here I have also horizontal loads on the columns and some more horizontal loads on these triangular loads on the gable girders. Same on the other side, and the same also for load case 5. Here they are a little smaller. Okay, now we can go into the timber design. You can find RFTimber Pro in the data navigator on the left side. Usually it's somewhere in this list. I added that to my favorites here. And also you can find it using add-on modules, Design Timber, RFTimber Pro. So here I want to do a design for all sets of members, so my girders, but I don't want to design all members, so I select the ones, and especially not the girders again, so I have to select the members one by one. I click these one by one because I don't want the bracing to be selected. Doesn't matter though. The program is not able to design it, or the module. Okay, I've selected my members to be designed. Then I select the standard I want to use for the design. In this case, Eurocode 5 with the national annexed DIN for Germany. And I have a quick look at the parameters of this national annex. Here I want to turn on the increase of bending strength for a height, for glulam with a height of smaller than 600 millimeters. Okay. And I have to set some details. For stability, I want to use stability analysis according to second order theory, which requires a definition of the imperfections in RFEMu, which we have done, so we can do that. And also using this register other, I want to set a maximum allowable design ratio for the cross-section optimization I'm going to do. So we have some reserves later on, so I can quasi manually have a look where I can still optimize the structure. Okay. Of course, I have to select some loads. So result combination number 1 for the ultimate limit state, and serviceability, for the serviceability limit state, I use the result combinations 2 through 4. Then I go on to materials. Here, only my glulam timber is can be designed. The steel can be designed in Timber Pro, of course. I go on to the cross sections. Here I find all the cross sections I have used in the model, and I want to optimize this cross sections from the main girders. So width and height for these with a minimum of 120 millimeters with an increment of 20, and for the height also 120 with an increment of 20. And I also want to optimize the rectangular cross-section for the columns. Here, just the height, that's okay. So we can go on to the load duration in service class. Here we have, we can check what our load duration classes are, and we can check which service classes we are using. We have selected the service class right at the beginning, and we keep it at service class 1. Then we can go on to the effective lengths for the buckling, the regular buckling. We have already said that we want to do that according to second order theory. And for lateral torsional buckling, we leave that at member length. It's just for the coupling and the columns in this case. And since these are all hinged at both ends, we can just stick with that. For sets of members, we can't do a design for lateral torsional buckling that easily. That has to be done using different means. For example, I forgot the term in English. Let me have a look. No. Sorry. I'll go on. It's got to be done differently. And I have the option to have a look at the perpendicular tension for curved members. I'm not going to do that in this design case, but I'm going to make another one later on, because I want to do this design for the whole length of this girder and not just part of that. And I can only select single members, so I'm going to do that later. I'm going to show you. For the serviceability, I use the set of members. Sets of members are 1 through 6. The length is 23.182 meters. And the last window we have is for the parameters is for options to reduce the cross sections with notches or a shear force reduction. We are not going to do that today, but if you have questions regarding that, you can always get back to us. Okay, I'm going to do the calculation. Okay, the internal forces also have to be calculated. Now we are doing the Timber Pro design. And we have some results. We have a maximum design ratio of 86%, which is obvious because we said that we don't want to have a ratio higher than 90% for the optimization, and in this case it's these 86% for our girders, which have been reduced to 120 to 360, from 140 to 440. So it's gotten a little smaller, and for that it's calculated. Our couplings don't really get any usage, 8%, that's basically nothing. So we could switch to a maybe cheaper material or to a smaller cross section, but we're not going to do that now. I've shown you how that works. Also, the columns have not been reduced. They are at a maximum design ratio of 77%. Probably if I go one size down to 100 to 180, then it would be a small amount above 90%. So this has not been reduced, but I can do that manually. I go back to the cross sections, and since I still have to have a look at the perpendicular tension, and I want to have a little reserve for that, I increase the height of my my girders a little, and I decrease the height of my columns, since I know that they can be a little smaller. And since I've changed that now, I have to give these cross sections back to RFEM. I exported all of them to RFEM, and I have to recalculate that, of course, because this is going to have an impact on the deformations especially, and on deformation design, serviceability. So now the calculation is quite fast. So let's have a look at the design ratios now. Cross section is best. So I've increased the height of this rectangle, so it's gone a little down, the usage, from 86 to 83%. Serviceability is at 37%, so that's not a problem. And for the columns, we are now at 95%, which is a pretty good usage. Okay, I make another design case now. New case for the perpendicular tension. And for this, I have created a member number 109, which is a result beam. I'll show you right away. Let me just add these loads. I just want to have the result combination number 1. And member number 109 is a result beam which I placed right next to one of these girders. It's 1 centimeter besides that, because I would get problems if I would set it in the same place. But so now it gets the correct internal forces, and I can do the design. The internal forces come from the girder. And I go back to Timber Pro, design case 2, member number 109. My result combination has vanished, obviously. And now I just need to go to the curved members. can activate the design for member number 109 with these factors, do the calculation. Oh, that's the problem. I have added the result combination number 1 to the serviceability limit state. Okay, I hit calculation again, and now I can look and see that I have a design ratio of 72% for the tensile stress perpendicular to grain and shear. So that's it for the presentation. We've covered the basics of the timber design using Dlubal products. There's obviously still a lot more that can be done regarding the design of timber elements. And I want to show you our website. Here you can access quite a big range of older webinars over supported learning webinars. And down here you get lots and lots of webinars, 72 in the end. So I think you'll find something interesting there. And also under support and learning, you find lots and lots of frequently asked questions and knowledge base with technical articles, where you can also find very interesting articles about timber design. For those of you who have not yet used our programs, feel free to download a free 90-day trial version, which you can use to test our programs thoroughly and then later on buy it if you like it. Thank you, Bastian, for your assistance and for answering the questions. If you didn't get an answer yet, we'll follow up, send you emails. Thank you for your attention and have a nice day. Bye-bye.